In this experiment, we'll add an initial velocity of 0.85. We'll change the initial position to be 1.5. And we'll keep the same inclined angle of 5 degrees. We'll run the experiment. And again we'll record the values of the puck's position along the one-dimensional path, every 0.1 seconds. And we'll plot position versus time. At time 0, the position of the puck is 1.5 meters. At time 0.1, the position of the puck is 1.581 meters. At time 0.2, the position of the puck is 1.653 meters. At time 0.3, the position of the puck is 1.717 meters. And so on, all the way down to time 3.0, where the puck is at 0.206 meters. If we connect these points, we get a graph of position versus time, that looks like a parabola. Let's try to write a mathematical equation that will fit the points in the line graph that we saw in the previous slide. This graph looks like a parabola. Therefore let's propose the equation, x is equal to c2 times t squared, plus c1 times t, plus c0. At time 0, the position is the initial starting position, which is 1.5. And so substituting 1.5 for x, and 0 for t, into the above equation, we get that 1.5 is equal to 0 plus c0, which implies that c0 is equal to 1.5, which is the initial position x0. Next we choose any 2 points on the curve, so that we can write two equations with the two unknowns c1 and c2. Let's choose the time to be 1 second and 2 seconds, in order to make our calculations easier. At 1 second, the position is 1.923, which implies that 1.923 is equal to 1 times c2, plus 1 times c1, plus c0, which we just found to be 1.5. And similarly at time 2 seconds, the position is 1.492, which implies that 1.492 is equal to 2 squared or 4 times c2, plus 2 times c1, plus 1.5. Equations 1 and 2 are two equations with two unknowns, c1 and c2. Now let's solve these two equations for c1 and c2. Multiplying the first equation through by 4, we get equation 3. And multiplying the second equation through by -1, we get equation 4. Now adding equations 3 and 4 together, we get 7.692 minus 1.492, or 6.2, is equal to 4 minus 4 times c2, or 0 times c2, plus 4 minus 2 times c1, or 2 times c1, plus 6.0 minus 1.5, or 4.5, which implies that c1 is equal to 6.2 minus 4.5, over 2, which is 0.85. Note that this is the same as the initial velocity, so c1 is equal to v0. Next, substituting 0.85 for c1 into the first equation, we get 1.923 is equal to 1 times c2 plus 1 times 0.85 plus 1.5, which means that c2 is equal to 1.923 minus 1.5 minus 0.85, which is equal to minus 0.427. So the equation which defines this curve is x of t is equal to c2 times t squared, plus c1 times t, plus c0, where c0 is equal to x0, which is 1.5, and c1 is equal to v0, which is 0.85, and c2 is minus 0.427. In the last slide, we derived an equation of motion for a puck on an inclined rail, with an initial velocity. The equation is x of t is equal to c2 times t squared, plus c1 times t, plus c0. Where c0 was found to be equal to the initial position x0, which is equal to 1.5. And c1 was found to be equal to the initial velocity v0, which is equal to 0.85. And c2 was found to be minus 0.427. Now let's derive the equations for instantaneous velocity and instantaneous acceleration. For instantaneous velocity, v of t is equal to dx dt. And so substituting the expression for x from the previous equation, we get the derivative of c2 times t squared, plus c1 times t, plus c0, which is 2 times c2 times t, plus c1, which is equal to minus 0.854 times t, plus 0.85. The equation for acceleration is a of t is equal to dv dt. And so substituting the expression for v from the above equation, we have the derivative of 2 times c2 times t, plus c1, which is equal to 2 times c2, which is therefore equal to minus 0.854. Note that minus 0.854 is equal to minus 9.8 times the sine of 5 degrees, where 5 was the inclination angle of the rail relative to the horizontal. Therefore we can rewrite the acceleration equation as a of t is equal to g times the sine of theta, and the velocity equation as v of t is equal to v0 plus g sine theta times t. And finally, the position equation can be rewritten as x of t is equal to x0 plus v0 times t plus 1/2 of g sine theta times t squared, where g is equal to minus 9.8 because the x-axis is pointing upwards. We can repeat this experiment, varying theta, and find that the acceleration is always given by the equation a of t is equal to g sine theta. Compare these equations of motion with the ones from the previous experiment, where there was no initial velocity. And we can see that the only difference is in the v0 terms highlighted here. So if the initial velocity is 0, that is, v0 equals 0, then these terms drop out, and you have exactly the equations we derived earlier. Here is an overall summary for this section. Objects moving horizontally, with no external influence, such as air resistance and friction, obey the 1D constant velocity equations of motion, which implies that the acceleration is equal to 0, which implies that the velocity is constant, and that the position is equal to the initial position x0, plus the initial velocity v0, times the time t. Secondly, objects moving vertically, with no external influence except gravity, move at a constant acceleration that is equal to the acceleration of gravity. So the acceleration is equal to g, where g is either positive 9.8, if the x-axis is pointing downwards, or negative 9.8 if the x-axis is pointing upwards. The velocity is equal to v0, plus g times t, and the position is equal to x0 plus v0 times t, plus 1/2 g times t squared. Lastly, we found that objects moving on an inclined linear path, again with no external influence except gravity, obey the constant acceleration equations. A of t is equal to g times sine of theta, where theta is the inclination angle of the path with respect to the horizontal direction, and g is again positive or negative 9.8, depending on the x-axis orientation. The velocity is equal to v0 plus g sine theta times t, and the position is equal to x0 plus v0 times t, plus 1/2 g times sine theta times t squared. Note that these equations of motion are the most general case. If theta equals 0, meaning that the path is horizontal, then the sine theta term is 0. And these equations reduce to the equations in case 1. And if theta is equal to 90, meaning the path is vertical, then sine theta is 1. And the equations reduce to those in case 2.